Okay. Hello, everyone. My name is Alex Smith. I work at the Broad Institute of Harvard and MIT as a computational biologist. And today I'll be showing you how to do some basic manipulation with two Python libraries called Numpy and Pandas. They're both very useful for doing science, and I'll show you how. A quick note on this presentation. Previously in this online lecture series, there have been some other Python tutorials which were done in Python version 3. For this, I wrote in Python version 2.7. There should not be many differences. I think the only difference you'll see is how print statements can be written. In Python 3, you need to put your print statements in brackets. In Python 2, it's a little lenient with letting you just say print something. So I generally use the latter here, so please don't be confused by that if it comes up. Part 1, NumPy. NumPy is, in short, a module for doing math in Python. Now you may think, well, Python already can do math, and that's right, but sometimes you'll want to do math on large groups of numbers. You'll want to do, say, linear algebra on vectors and matrices, as you often will in data science and statistics. And NumPy provides utilities and objects for doing this that are much more robust and versatile, at least for math, than Python's default list object. So I'm going to start with an example. This example is done in regular Python without NumPy. We're going to take a list of diameters, the distance across circles, and we're going to write a method that gives the areas of those circles based on their diameters. So we start out by importing pi from Python's built-in math module. We initialize a list of diameters, 0 to 9. We initialize our areas, and we write a for loop, which for each index in areas, it multiplies pi times half the diameter of each circle. We need to make those floating point values. A floating point is a data type for a number. It just means a decimal value rather than an integer value without a point after it. You'll notice that in our declaration of diameters we have integers, and in our output we have decimals, so we need to make sure to specify those floating points in the division. And of course it's pi r squared for the area of your circle, so we have the squared operator, the exponent operator rather, in Python to the second power here. And we print them out. And we successfully get the diameters we're looking for. As a check, we can look at the diameter 2. We know that divided by 2, that's just 1. So we get pi times 1, and we get pi for this value. So we can do that, but there are some issues we might like to make a little smoother. First of all, there was the issue I just discussed with the range function in Python generating integers. We had to do all this extra bookkeeping to make sure that it didn't round to the floor when we divided by 2, and we'd probably like to avoid that. Unfortunately, there's no way to force range within range to output floating point numbers. Also, we had to write this for loop just to do math that could be done on one line if you were just writing math. It's a property in math that if you multiply a scalar value like pi by a vector, an arrangement of numbers similar to the list we initialized with diameters, it's a property in math that if you multiply a scalar by a vector, you get a vector with each element of the vector multiplied by the scalar value. So why do we have to bother with this for loop? Let's try doing it the way we do in math. Let's just try writing that straight into Python and see what happens. So here we say, okay, this list here, we'll just treat the list as a vector. And we'll multiply our scalar value by the whole list, square it, see what happens. And perhaps unsurprisingly, we get an error. So yeah, in math, the product of a scalar and a vector is a vector, but we're not multiplying a scalar and a vector. We're multiplying a floating point number and a Python list object. And the product of those two things is an error. So if only there were some data object that could more closely represent a mathematical vector. Well, there is, and NumPy has it. Here, if you're not familiar with the import statement, this is import NumPy, a module I've installed in Python, as NP. And NP is an alias for NumPy, so that when I want to call NumPy functions further on, I don't have to type NumPy every time, I can just type NP. Here we declare the diameters, and we use our first NumPy method, a range. A range is just like Python's range, except you can give it a data type. So I specify that I want my range from 0 to 9 to be floating point numbers. And accordingly, in the printed statement here, we see we get floating point numbers from that, which saves me having to do the bookkeeping here and making 2 a floating point so that it knows not to round. And for areas, I do just what I tried to do in the last slide. I multiply pi, which NumPy knows, straight by the array object here, divided by 2, and I square it. And it knows what to do with that. We get the same results we got when we used our for loop, but with this much simpler statement that you'd write as you would write it in math. What we initialized when we called NumPy's arrange function was not a Python list object, but an object specific to NumPy called an ND array, like n-dimensional array. And that is the nice, flexible, powerful object we are now working with, and we can do math with. As the slide says, it saves us some bookkeeping, and it has a lot of different methods. And there are several different, what we would call constructors for the ND array in NumPy. Constructor just means it makes an object. So let's look at a few of them, commenting these lines. So here's what we just did. NumPy.arrange, if you just give it an integer argument, it'll count up to that integer. So there, it's identical to Python's range method. If we give it that integer and then also give it data type float, it'll give you floating point values, like in the last example. Here, I give it a start, a stop, and also a step. The step tells it how much to increment in its count, and since I gave the step as a floating point value, it gave an identical result to this line. And also, something you can't do with range. Also, something you can't do with range is do decimal values under 1. So I give it a start value of 0, a stop value of 1, and an increment of 0.1, which gives us an array of values ranging from 0 to 0.9. There's also a similar constructor to arrange called linspace. I encourage you to give it a try if you start coding some NumPy on your own. It's very handy. So why was it that our circle example worked? It's because NumPy has a built-in operation for when you multiply things by ND arrays called broadcasting. So we saw that for the circle example, broadcasting behaved just like the multiplication of a scalar by a vector in math. So you might be curious, well, how does this work once we're multiplying ND arrays by other ND arrays? So we have a few examples for you here. Here I've constructed a few ND arrays similarly to how you saw in the last slide. We have x1, 2, 3, y4, 5, 6. So let's multiply them by each other and see what happens. We get 4, 10, and 18. So we see this was done element by element. 1 times 4 gives 4, 2 times 5 gives 10, and 3 times 6 gives 18. Let's do their sum. Can you guess what they'll be? 1 plus 4 equals 5, 2 plus 5 equals 7, 3 plus 6 equals 9. And let's do the quotient and difference. We also see these are done element by element. 1 divided by 4, 0.25, 1 minus 4, negative 3, and so on. So for 1D arrays in NumPy, it goes element by element. And in fact, that's a good guess as to how arrays of any shape will broadcast when you perform basic operations on them. So a critical difference between lists and ND arrays is that ND arrays are homogeneous, which means that you can only have objects of one data type inside them. Here, I initialize a Python list, and here I initialize an ND array. In the list, I put a few different objects. I put a string, I put a floating point or decimal number, I put this Boolean, does 0 equal 1, and I put an integer, 7. And we see that it has no problem printing out the string as I put it in, floating point number, the result of that Boolean, and 7. But for y, I initialize an ND array. If I print y, let me move that so it's easier to read. Nope. Also no. Let me keep track of where I am here. Here I'm taking a closer look at the before and after of y when I try to assign a floating point number to one of y's indices, even though I declared it to be an ND array of integers. So this is how it was originally. And with this command, I tried to set the last index to the value 2.5. Well, ND arrays are homogeneous, so it stayed as an integer. So when you try to pass 2.5 as an integer, it rounds to the floor and becomes 2. You can also nest ND arrays within ND arrays. That is how you get ND arrays and not just 1D arrays. Let's start with these. With these constructors, I initialize two 1D arrays. X goes from 0 to 9, and Y goes from 10 to 19, as you saw with previous arrange examples. Then I make Z a combination of these two with the NumPy's vstack command, which is one of many ways to sort of just stick arrays together in a manner which you'll soon see is pretty intuitive. Let's see what comes out of it. I printed the dimensions of Z, so we now have a 2-dimensional ND array. I printed the shape of Z, 2 by 10, returned as an object called a tuple, which is like a list, but in parentheses instead of square brackets. And finally, here's what Z looks like. It's printed kind of like a list of 2 lists, or rather an ND array of 2 ND arrays, where the first ND array is X, as it was declared up here, and the second row, or ND array, is Y, also as declared. I should add we can now give Z pairs of coordinates and look at different values. So if, for example, we want to look at row 1, column 5, well, we'd give it index 0 for row 1, because Python is 0 indexed. And for column 5, again, because of the 0 indexing, we'd give it column 4. So we expect to see the number 4 here. And indeed, we see 4. some other constructors for NumPy. Let's start with numpy.ones. Here I have numpy.ones 10. What does this do? It creates an ND array of ones, and it gives you the number of ones you specify. That's pretty straightforward. What about numpy.zeros? Well, following the previous example, you might guess, gives you the number of zeros you specify. And actually, for both zeros and ones, if you pass as an argument this type of arrangement called a tuple, which is a list of comma-separated numbers between parentheses, then that'll determine the shape of an output matrix rather than the number of elements in an output 1D array. In this case, I gave it the tuple containing 10, 10. So it made it 10 wide and 10 high. There are also some constructors called ones-like. There's also one called zeros-like, and you pass it an ND array as the constructing argument. So I have my table of zeros here set as y. So what happens if I give it ones-like y? Well, it gives a matrix or an ND array of the same shape filled in with ones. Often what you'll do is initialize a matrix like that and then custom set the values with another further function. Just as an example of how broadcasting works with larger ND arrays like this, I'm just multiplying 2 right by this ND array. So what happens? Well, as you might guess, multiplying it by 2 multiplies every element in it by 2. A little more broadcasting, this time between 2D arrays. A little more broadcasting, but this time between 2D arrays. I initialize a 2D array x. Let's print x. It looks like this. 1 and 2 in the first row, 3 and 4 in the second row. I initialize another ND array called y. I use the constructor identity, which gives you the identity matrix. If you don't know what that is, you're about to see it. It has ones diagonally through it. And it has the property in math that if you do proper matrix multiplication and multiply it by another matrix of the same size, it just gives you the matrix you multiply it by. It's kind of like multiplying 1 by a scalar value. You just get that scalar value. So let's look at what happens when we just broadcast them together with a multiplier. Well, if it were following what we expect from math for matrix multiplication, then we would just get 1, 2, 3, 4. Obviously, this is not that. So broadcasting for this does not do what we would straightforwardly expect from math. Rather, it does, as we see, element by element product like it did for our 1D arrays. It gives us 1 times 1, 2 times 0, 3 times 0, 4 times 1. The proper thing to use for 2D arrays is numpy.matmul for matrix multiplication. When we do that, we get what we expect, 1, 2, 3, 4, multiplication by the identity matrix. A more general mathematical multiplier for ND arrays of any dimensionality is numpy.dot, which for 2D arrays will also do matrix multiplication. There are many other constructors for ND arrays I haven't touched on. you can read them in the NumPy documentation if you do any further practice. So I'll give this same link again at the end of this presentation. I'll go over one more here, which is how to initialize a NumPy array from a file on your computer, because you'll often have a table or a text file full of numbers that you just want to put right into an array. Here on my desktop, I had a file called somenumbers.txt. It was just lists of numbers delimited by commas. In the first row, I had 1, 2, 3. In the second, I had 4, 5, 6, and so on. So NumPy reads it straightforwardly. We have a 2D array, 1, 2, 3, 4, 5, 6, 7, 8, 9. With practice, you'll find eventually that you can do pretty complex linear algebra and statistics and all sorts of great stuff with NumPy in addition to other modules. Notable ones are SciPy and Matplotlib, which together have graphing and statistical utilities that are really great. And in fact, they rely upon NumPy for many of their methods. Another example of a module used for data analysis and manipulation is Pandas. So how does this differ from NumPy? Well, NumPy we saw dealt just with numbers and just with homogeneous data. So what if we want something more powerful than Python's list object, but we don't want to do just numbers? You'll notice that I never had any headers or anything for the ND arrays I showed you with NumPy. We just have the numbers, and the only bookkeeping we were able to do for them was to assign them variable names in the code itself. Well, often you'll have very large tables of text data, sometimes text mixed with numbers from column to column. And for manipulating files like that, for looking through them quickly, for aggregating data from such tables, or grouping them in different ways and forwarding and saving only what you want, Pandas is really the go-to utility for doing that with Python. Here, another import statement, import pandas, and I give it the alias PD. And I have a table, a comma-separated value text table on my desktop called Stooges, which is data about the Three Stooges, a American comedy act from the early mid-20th century. So I read it and I output it. And this pandas.readCSV method, it outputs an object called the data frame. And the data frame is kind of to Pandas what the ND array is to NumPy. It's its big flexible object that everything sort of revolves around. So reading the CSV as I wrote it, well, we can see what it looks like, but we see there are some problems. In that CSV, I did not write a header row. I just had the data in there. So it thinks that the first row, Pandas thinks the first row was the headers for that. And obviously, these are not headers. These are data. In addition, because sometimes the data you get isn't perfect, I left out a value, Larry Fine's final appearance year in the Stooges, and I also put in an incorrect value. The year 2183 hasn't happened yet, so that can't be the last time Curly Joe Dorita appears in the Three Stooges act. We'll start by looking at that header. To fix the header, it's pretty simple. We use the same argument to import the data to a data frame. The same method, I mean, but we give it an additional argument called names. And to names, we pass a Python list. So I want my 3 columns to be labeled Stooge for the respective comedian, first appearance, year of first appearance, and final appearance for the year of final appearance. Let's see how that turns out. Looks good to me. So that works okay for a small table, but with data you'll get in science, you often get very, very large tables, such as lists of 600,000 genetic variants, each with their own respective set of summary statistics. So for those, you don't want to load all those into memory at once and display them in a window. For those, you might just want to peek at the start or finish of them, just to make sure the first or last few rows look like what you expect them to. So here, I do a command which is associated with the data frame object I called stooges, called head. And I give it the number 1, so it gives the first one thing that appears in that data frame. Here, I give it the argument tail 2. You might guess what this does based on how head behaved. It gives the final 2 values in that data frame. You can also return things other than the start or finish. Sometimes you want things from the middle or all throughout. So I'm curious about that missing value. I want to know what type of thing it is. I want to take a closer look at it. So let's break this down. In the first set of brackets, I specify what value I want from the row. So I want the date of final appearance, because that was where the missing value was. And here, to filter for what I want, I use a Boolean value. A Boolean is a true-false, if you don't know, evaluated with this equal statement. So we look at stooges. We want to see the stooge, and the stooge we're looking for is Larry Fine. So let's enter this. And it comes up with the correct thing. It comes up with NaN, not a number, for the empty value. It's in the column final appearance, and its data type, it turns out, is a 64-bit floating point number. So it's treated as a decimal. Now let's filter for the starting 3 stooges, the ones who debuted in 1930. This is a similar Boolean to the one I had last time, except now I'm doing one for multiple objects instead of one, because multiple objects correspond to 1930 for the initial year. Since I have nothing in a first set of brackets, it just gives all the values for things that match first appearance 1930. So from that, I get the original 3 stooges, Mo Howard, Larry Fine, and Shemp Howard. As I pointed out, the year value I had for Curly Joe Dorita was quite an error. So maybe we would give a different sort of Boolean to filter stuff like that out. In this case, I put final appearance because that's where the error occurred. And I say, okay, keep it to 20th century or earlier, because they were a 20th century act. And not only does that filter out Curly Joe with the error put in for his final appearance, but it also filters out the empty value for final appearance for Larry Fine, because that can't be compared to 2000 because it's not there. So what we end up with here is a set of data that we've basically performed quality control on. And say if we're one stage in a multi-stage analysis, this data would be ready to be passed on to the analysts downstream from us. So let's do that. Let's save it to a file to pass to the analysts. We take the name we assign the data frame, and we use the data frame function to CSV to write it to something. I give it a file path. I want to call it stooges fixed. I put in header.true because I want the header we gave it in pandas to be saved to the text file itself. And I give index equals false so that these numbers, the indices, won't be included in that text file. They're useful in pandas, but they're not useful for the text file. So I put that in. I'll go to my desktop and we'll take a look at it. And here's what came out. As we can see, it looks like we would expect. And that's it for my introduction to both of those modules. I hope these gave you an idea of the beginning of what they can do, but really I've just scratched the surface of the full range of their capabilities. Included here are links to the introductory pages for both of them. If you want to learn to use them, I really encourage going there and learning to do so. They're very powerful, very useful once you learn to do them. If anyone likes, I can also email anyone a copy of the code in this presentation. Thank you very much for listening. I appreciate your attention.